Welcome to another section of Chapter 7, Static Equilibrium or Extended Bodies at Rest. So far you've already observed situation where several forces acting on a system or a body and the system did not move. We're gonna talk about those conditions in this particular section. So let's take a look at this little warm-up here. So you have three pictures hanging on a wall, which one has the greatest tension force in the two wires. So give yourself some time to think. Apply the second law. So using the second law, you look at the support tension. So if you're gonna look at the components, you have x and y components of the tensions for this. So you're gonna look at the x. All of the x would be technically gonna be equal. However, if you look at the component on the y for this are gonna be different. So your answer should be this one. This one will hold the greatest tension given that the angle is greater from the others. So we're gonna look into that. Objects that are being acted upon by forces, two or more forces, and these forces will give a net force of 0, and we're going also to find this force that will cause the object to be not in motion, or what we refer to as static. So we are talking about statics in here. So we are dealing with conditions for equilibrium for objects to be at rest. So let's start with the first condition. So the first condition for static equilibrium is that for a body to be in that state, all the sum of all the forces, given that force is a vector quantity, and therefore the sum of the forces must be equal to 0. So sum of all the forces must be equal to 0. The sum of the forces on the x must be equal to 0. The sum of the forces on the y must be equal to 0. So always think about that. So let's take a look at this example in here. So you have a picture with a mass of 4 kilogram hangs on a wall. What are the magnitude of the tension that are held at 40 and 50 degrees? So in order to solve this, we're gonna always apply the pi method. So we're gonna draw a picture of this. So we have a picture, we're gonna draw information. So we're gonna use a free body diagram. So let's draw a free body diagram for that. So drawing the free body diagram, let's label this as tension A and this one as tension B. And drawing the free body diagram, we have tension A here and at 50 degree, and then tension B here, and we have the force of gravity of the picture frame. So that's our free body diagram. So solving for the forces on the x, so forces on the x is TBX and then TB minus TAX, since it's going in that direction, so we use the coordinate system. So if we're gonna look for one of the tension, let's say we look for the tension on B X, so we will have this equation. Now let's solve for this forces on the y. So solving for the forces on y, so we have TAY going up, so that's positive, same as B, and then we have the force of gravity, so plugging in how to find the component of that, so that's TA sine 40 and then TV sine 50 for the tension on B, and then rearranging the equation, knowing that TB is equal to cosine 50 times T sub A over cosine 40 degrees, then we could plug that in. So in this case we're solving for two unknowns, so we're gonna be using two equations. So we're plugging this first equation that we've derived on this, and that's what we have here. So solving for T sub A, we end up with third unit. Your answer should be approximately around this answer. Then again, The AP1 exam is not going to be concerned on how exact you are in terms of your calculation. They're going to be looking for how did you arrive at looking for the tension forces. So applying the algebra and your trigonometric knowledge on this, trigonometry knowledge on this. So let's look for now the tension on B. So we could go back to this equation here and then plug in the value of T sub A. Then you should get an answer of 25.2 newtons. So that's how we solve for the first condition of equilibrium. So draw a free body diagram. You could also make a table of the forces. You can make a table of that forces and solve for two unknowns. So you must have two equations and you plug that into this. Now let's have one more problem in here. I want you to look at this and I want you to spend some time, and we're going to apply static equilibrium. At this time we're going to find the angle to which it was raised. So we assume that there are no non-conservative forces acting on the object, so an isolated system. So solving for this, we draw a free body diagram and we look at that there will be components of the force. So this applied force will be equal to the component of the tension on the X, and then we have T sub Y, which will be the Y component of the tension. So let's look at and apply the second law. Sum of the forces on the X is equal to 0. So the force applied to raise that at a certain angle is equal to T sub X, which is equal to T sine theta. So we could ignore this and we could go to the summation of the forces on the Y to find theta. So given that T sub Y is the positive going up minus the weight of the object, rearranging the equation, solving for theta, then we could find this, and solving for the angle you should get about 54 degrees. If you have questions, let me know. And that's for the first condition on equilibrium. Now let's look at the second condition for static equilibrium. So the sum of the torque must be equal to 0. So if you have the torque, so if you look at this object, the torque that moves in the clockwise direction, so sum of the torque on the clockwise direction must be equal to the sum of the torque in the counterclockwise direction. So if we say that the counterclockwise direction is positive arbitrarily, and then we say that the clockwise direction is negative, and the sum of them would be equal, then the object will attain a static equilibrium. So let's practice trying to find out, so what would keep this in a static equilibrium. So how would this abide with the second condition for static equilibrium, that the sum of the torque would be equal to 0. So first we're going to draw the force body diagram. So that is the force body diagram. So we look at the sum of the forces on the Y. So looking for the forces on the Y, so we have the normal force that is acted upon by the fulcrum, that's where it's going to pivot, and we also assume that the board is uniform and centered over the axis of rotation. So looking at these forces, we have force of A is equal to mass times G, and that gives us the forces equation. Now let's look for the torque equation. So we're going to calculate, so how far would this girl sit so that they would balance this seesaw. So we're gonna look at the lever arm relative to the pivot point. So, and we're gonna find for this X here using the second condition for equilibrium. So solving for the torque, on this particular problem. So we have the force, which is equal to mass times g times the length of the object from the pivot point or axis of rotation, and then the torque of B2, and then we could also factor out the g, so we plug in the values, rearranging the equation to solve for x. So we have ma over mb times the length of the object A, and you should get 3 meters. So she should be on the seesaw sitting at about 3 meters away, so about 0.5 meters, a little bit farther from the axis of rotation compared from the boy. That's it for second condition.